Hey guys, Miss Crutcher here. I just wanted to give you guys a lecture today on potential energy. Sorry I can't be there with you guys. I should be back next week. So what we're going to look at today is potential energy. If you remember from the other day, we looked at kinetic energy, and kinetic energy was that energy of motion. So today we're going to look at the difference, or the opposite of that, which is going to be the stored energy or that potential energy. So potential energy is your energy due to a position. So here you have a dart gun. You can press it back. The spring changes position. So it's going to give it energy so that way you can fire it. You have a bow and arrow over here. You pull it back. Same thing. You're going to pull it back. So you're going to do work on the object to make it move, that force in the distance. And then when you let it go, the arrow is going to go flying. The other type over here, you have a person on a swing going back and forth. Same thing, you have that height. So he's going to have potential energy due to his position. So the first type of energy is gravitational potential energy, or GPE. Okay, your gravitational potential energy is the formula for it is mgh, and the m and the g, if you remember, is your weight. So with these problems, if they give you the weight of the object, you can just plug it in as m and g. If they give you the mass, you can multiply it by gravity and still get the same value. Your height for these objects must be in meters, and your GPE is going to have units of joules, just like work and kinetic energy that we've looked at. So your gravitational potential energy is based on your height and your mass. So if you compare you to a little kid, if you both fall on the ground, the little kid's not going to get hurt as much because they have less height to fall and they have less mass. If you wanted to increase your potential energy, you could climb up on your chair, climb up on the desk. You're increasing your height, so you're increasing your gravitational potential energy. With gravitational potential energy, it also does work. So what that means is that if you increase the work or increase the height in something, you can cause it to move a different distance. So we have another equation for work, and that becomes work equals the potential energy final minus your potential energy initial. Remember, anytime you see this delta, it always means final minus initial. So your work can be equal to your change in kinetic energy, force times distance, or change in potential energy. Okay, the thing we're talking about here is the work being done by external forces. So that means that it's an outside force, so somebody else is pushing on an object to make it move up. So when you swing, for example, your legs are physically pumping, you're moving back and forth to make you move up. So that would be the work being done. The other important thing about potential energy is that it's only looking in the vertical distance. Okay, remember, when you think back to work, you were looking at the force and the distance having to be parallel. Well, in potential energy, we're looking at gravity. So gravity acts up and down, which means we're only looking at the path in the vertical direction. So this horizontal distance that you move here means nothing. Okay, the only thing we're worried about is this height factor over here. And that also means that no matter who you are, Stratford, if you climb from the first floor up to the third floor, it doesn't matter which room you're in, your potential energy, that height value is going to be the same because you all started on the first floor, you all ended up on the third floor. Which room you're in, it doesn't matter if you're in my room, an English room, a history room, one of the other science rooms, your height change will still be the same since you went from the first floor to the third floor. Okay, let's try a sample problem. So in your homework, this is problem number 32, and you have a spoon being raised 21 centimeters above the table. That's important because remember, height is relative. So I could have told you the height of the table and then told you how high above the ground the spoon was. So they're just telling you their specific reference height. So that's the height that it's actually moving that you'll want to care about. if the spoon and its contents have a mass of 30 grams, what is the gravitational potential energy associated with the spoon at that height relative to the surface of the table? So what you have first is to write down your givens. Okay, you're given the height in centimeters. So you have to convert that to meters just like you did on that Power Lab. There's 100 centimeters in a meter. So 21 divided by 100 gives you 0.21 meters. Then the other thing you're given is this grams, which would be your mass. Same thing with the height. We don't work in the unit that they give it in. We don't work in grams. In this case, we want to convert to kilograms. So there's 1,000 grams in 1 kilogram. So again, divide by 1,000 this time, and you'll get 0.03 kilograms. The unknown in our case is going to be this gravitational potential energy, or GPE. So we're going to use that new formula from today. GPE, or PE, equals mgh. We do not have to manipulate the equation since it's already solved for potential energy, so plug it in and solve. Remember, G is 9.8 meters per second squared, and use those converted values that you got. Okay, once you do the math, multiply it all together in your calculator, you should get 0.0617 joules. Okay, hopefully it's not too difficult. This is a pretty easy formula, so it's pretty nice. I like this equation for that reason. Okay, the next problem is 33. So similar situation, you're going to calculate the increase in gravitational potential energy of a 75 kilogram hiker who climbs a peak of 1,500 meters. So again, write down your givens. So you're given the mass and the height. So the kilograms telling you that that's the mass, meters telling you that that's your height. Look for your units. Again, you're solving for gravitational potential energy, your GPE. So you can use that equation from today again. PE equals mgh. You don't have to manipulate it, so plug it in and solve. 75 times 9.8 times 1,500. And you get 1.103 times 10 to the 6th. If you want to leave this out in out of scientific notation, that's fine with me. If you want to put it in scientific notation, whichever one is easier for you. Okay, so this is the first type of potential energy. Now we're going to look at the second type. So the second type of potential energy is our elastic potential energy, or EPE. And in this case, we're looking at what happens when an object is stretched or compressed. So some examples of that would be like a spring or a slinky, bungee jumping. It has that cord that's going to pull you back. The springs in a bed compress when you lay down on them. The springs in a car. Okay, all of those would be different examples. In all of those cases, something is going to be pushing down on some sort of spring to compress it. You have a bow and arrow. Okay, guns, for example, all follow that same thing. The other thing is that they can do work on a second object. So when you compress like the spring in a dart gun, it's going to do work on the dart when it fires it, because it's going to apply a force going to the right in this case, and the dart is going to move to the right, so work is being done. With the bow and arrow, you pull it back. When you release it, it's going to apply a force on the bow, or on the arrow, excuse me. And the arrow is also going to move, so again, doing work on another object. Okay, with the spring, what we have to worry about is the fact that springs, when you set them down by themselves, are going to have a normal amount that they're going to stretch. So we call this the relaxed length. Then once you attach some sort of mass or weight to it, it's going to stretch even more, or this could also be your force pulling it down. So the distance x that we want to use in this equation is really going to be the stretched length minus the relaxed length. So when we look at this equation, what we're really looking for is how far did it stretch. So if you can see on this one, it stretched 5 meters. This would be your 0.5 meters. That would be your relaxed. Then it stretched, and so it stretches a meter. So if you look at this equation here, you would take 1 meter minus 0.5, and so your unstretched, or your x value that you would use, would be half a meter. This equation is just another equation for forces, for looking at a spring as it pulls down. K is going to be your spring constant, and it's a measure of how stiff a spring is. So a slinky that's very, very bendable is going to have a very low value of a spring constant, versus like a car that's going to have a much higher value. So the stiffer the spring, the higher the spring constant is going to be. Okay, here's another version of that equation. We call it Hooke's law. The only thing that's different about this one is that this is really looking at as the force as being a restorative force. So the fact that it wants to bring it back to that relaxed length. So if you pull a slinky down, it's going to sit there and it's going to bounce up, bounce back down, and then bounce up and back down and bounce up and back down. As it sits there and vibrates and bounces up and down, up and down, up and down, this Fs is the restorative force. It's trying to bring it back to where it originally started. This force is not constant. If you take a slinky, pull it down, and then let it go, it's going to vibrate or bounce up and down a lot at the beginning, and then it's going to gradually slow down and slow down and slow down and slow down. So this force will not be constant. Instead, it will be decreasing over time until the spring eventually stops, and then the force will become zero, and it will be back at that original or relaxed length. Okay, so what we're focusing on really is this idea about your springs can store energy. So you pull a spring down, you can hold it there for a second, and it's going to store energy. So our equation is elastic potential energy, this EPE, and it is 1/2 kx squared. Okay, just like before, your K is going to be the spring constant, and X is going to be the distance that it stretches. Stretch from that equilibrium. Okay, and EPE is measured in joules because it's another type of energy. Okay, so again, we're looking at energy being stored so you can do it later. If you think back to like a bow and arrow, you pull the arrow back and you just keeps that energy until you let go, so it's being stored for a little bit. Okay, let's try a problem. You have number 36 in your packet. A spring with a force constant of 5.2 Newton meters has a relaxed length of 2.45 meters, and then you attach a mass to it and it comes to rest, and now it has a vertical stretch of 3.57 meters. Find the elastic potential energy. So if you write down your givens, you have a K of 5.2 Newton meters, and then you have an X relaxed value, and then you have an X stretched value. So you have two different distances. Okay. You're looking for the potential energy. So this is a two-step problem. The first thing you need to do is figure out your distance that it's stretched. So this delta x. So you're going to take your stretched value minus your relaxed value. So 3.57 minus 2.45, and you'll get 1.12. So this is the relaxed length that it's at originally. You add a mass to it, so it's going to become even more stretched. And again, the only distance I'm really looking for is the distance from where it originally was to where it is now. This is the x value that I want. Once I have that, I can use that equation for elastic potential energy, 1/2 kx squared. Again, I don't have to manipulate it, so plug it in and solve. Only the distance, that x value, gets squared, nothing else, so just be careful with that. And you should get 3.261 joules. Again, joules because you're finding the potential energy of a spring. Okay, your homework tonight is to do the rest of the potential energy sections. So the problems are listed are up on the board and on the front page of your packet, and I will be checking the homework over kinetic energy and the potential energy next class.